and practice of designing living and working environments in space. A suit port is a sort of an airlockless airlock. Now that may be more confusing, but basically, actually, some of my earlier designs are already in use. The most important thing is that human-centered design must be research-driven and evidence-based. Speaking to space architects now, always stand up for the truth.
Welcome to the Omar Alayli podcast, your go-to podcast for exploring the diverse fields driving space exploration and technology. I'm your host, Omar Alayli, and today I'm thrilled to be joined by Dr. Marc Cohen. Marc has dedicated his career to pioneering space architecture as both a scholarly and scientific discipline. With 4 decades in the industry, including 26 years at NASA's Ames Research Center, he has profoundly shaped human habitats in space by focusing on sustainable, functional, and human-centered design for exploration. Marc, thank you so much for taking the time to be here today.
You're welcome. Thank you for inviting me.
Great to have you. Marc, you have dedicated your life's work to the space industry, particularly to the development and advancement of space architecture as a field. Can you start by sharing with us a brief overview of your journey and how it led you to specialize in space architecture? And why have you chosen this path in the first place?
Well, I saw my first satellite, Explorer 3, in July of 1958. I was 5 years old. I watched it through a scientist's telescope and saw it sail across the lens. I wanted to make one myself. I was an avid follower of the 1960s space race. I built scale models of all the American spacecraft. Then in 1979, I took a job at NASA Ames Research Center as a facility architect. My official title was Aerospace Technology 801 General Engineer for Experimental Facilities and Equipment. They didn't have a category for architects per se in that organization. While I was there, I began freelancing design work for space station concepts, and that got me a trip to the Space Station Technology Workshop in March of 1983. From there, I was invited to join the Space Station Concept Development Group at NASA headquarters, joining as a commuting member. Back at Ames, we formed the Space Human Factors Office to support space station freedom, and I became a commuting member of the Concept Development Group. From Ames to Washington, D.C., and to other NASA centers and to various aerospace contractors, where I was traveling at least two weeks a month, sometimes 3 weeks.
You have been in this field for more than 4 decades. Is there a moment or event that when things got tough professionally, you fall back on in order to sustain you, and something that keeps you going and remind you that what you're doing is worth it?
Well, it's always challenging. None of space architecture ever comes easy to me, but there have been a few high points. At the Space Station Technology Workshop, 1983, I was the only person who brought scale models of a space station, my triangular tetrahedral concept. And the reason for that was that NASA headquarters had told Johnson and Marshall Space Center not to bring any models, but nobody told Ames, so I had a monopoly and attracted a lot of attention. And in the final panel, I was commended by one of the speakers from the stage. Then in 1986, at the American Society of Civil Engineers Earth and Space Conference, Buzz Aldrin came into my session while I was presenting on the distinction between an interplanetary vehicle and a Mars surface habitat. And he began asking me rapid-fire questions about the presentation. A few years later, Buzz invited me to join him at his sister's country club in Atherton, California. He expounded on his concept for an Earth-Mars cycler. More recently, I won the Gordon Woodcock Award in Space Architecture, the highest award in our field.
Marc, some of our listeners might not be familiar with the term space architecture. When you were at NASA Ames Research Center, you were designated as a flight systems design engineer or aerospace engineer. How do you define space architecture in your own words?
When we formed the Space Human Factors Office, my title was changed from general engineer to aerospace engineer for manned systems. And then later, when I went into Space Projects Division, it was changed to aerospace engineer, flight systems design. So how I define space architecture is that space architecture is the theory and practice of designing living and working environments in space. And that's the same definition as in the Millennium Charter from 2002, and it's my words. So,
So you mean to say the Millennium Charter, you wrote the definition for the space architecture you just said?
yeah, I contributed that sentence.
So let me ask you a follow-up question. Nowadays, has NASA adopted space architecture as a job title? And if not, why not?
No, they have not adopted space architecture as a job title. They do have a title for architect, and I believe that at Johnson Space Center, Chris Kennedy was classified as an architect.
Mhm.
But it's a limited position, only promotable up to a GS-14 as opposed to a GS-15 for all the other AST categories.
Okay. And in your opinion, is it an essential field for future exploration?
Yes, I think so.
Okay. Okay. Let me ask you this now. Were there any mentors that shaped your perspective on architecture in extreme environments? And how did they or their methods shape your perspective?
Okay, well, Buckminster Fuller was the closest to my having a mentor.
Mhm.
From high school on, I was a Fuller acolyte. I attended many of his lectures around the New York area, and when he gave his town hall series of lectures in New York in 1971, I stayed on stage after his talks and asked him questions about geodesics and other topics. And I have applied Fuller's Dymaxion principles in multiple ways, and those principles are anticipation, comprehensiveness, and design as science. Another quasi-mentor was Robert Maycall, the founder of system engineering. Robert was a member of the Space Station Concept Development Group at NASA headquarters. Later, he had several contracts to serve as an on-site consultant at Ames, and I came to know him and his wife Florence quite well. He reviewed some of my papers and presentations and gave me constructive criticism. I never bought into system engineering to the same extent that I engaged in geodesics, but I learned a great deal from Maycall's approach to system design. His approach was more comprehensive than Fuller's, and one of his favorite questions was, what are we not considering? Another mentor of sorts was Alan B. Chambers, the chief of the Aerospace Human Factors Research Division at Ames, in which we founded the Space Human Factors Office. His motto was, the only way to succeed in this business is to do the best work. I learned from him the importance of being available and responsive to new inquiries and opportunities. Then, at the Concept Development Group, Bryant Chamber, who is an MD and PhD, was the chair of the Human Factors and EVA team. I learned a great deal from him about the physiological and metabolic challenges for humans in space. At Ames, Mary Connors was the author of Living Aloft: Human Requirements for Extended Spaceflight. She was in the Human Factors division with me and gave me chapters from her book to review, and we had an excellent rapport. I still refer to her book Living Aloft for my work.
Great. Let's now move to theory and practice and the challenges that come with space architecture. Although space architecture is human-centric, this new field doesn't have centuries of built-in heritage to learn from and build upon. In addition, the data we do have come from highly trained an extremely small pool of astronauts, 280 as of 2024. And those astronauts have operated in space environments and short duration missions, averaging 3 to 9 months. How does these limitations and challenges affect the way you research, test, and validate new space architecture concepts, orbital or planetary?
Well, I take a scientific approach and apply the scientific method as much as is feasible. This follows Buckminster Fuller's Dymaxion principle of design as science.
Mhm.
The small number of subjects or a small sample size, a small n, as we say, is not such an impediment if you understand statistical research design. The main challenge is how to set up scientifically valid simulation experiments. This is a big topic and is extremely difficult to persuade people in NASA and the industry who are focused on specific mission simulations for training purposes.
Okay, let me ask you a follow-up for this. Why is it extremely difficult to persuade people at NASA and the industry who are focused on specific mission simulations?
Well, they just don't think of simulators as being a place to do experiments, especially in the human space exploration field. In the aeronautics field, the flight simulators, which are based on aircraft cockpits,
Mhm.
are much more available for experiments. But the whole concept behind experimental simulation is that you have to be able to vary
Mhm.
the conditions in the simulator, that the human environment interface in the simulator is a set of variables that you should be able to manipulate and control. And this is an alien concept.
How about analog astronaut? Is it considered part of a simulation? Do you consider that?
They are simulations, but typically the way these analog facilities work, whether it's the Hawaii one or the Mars Desert Research Facility,
Hmm.
they're all used for mission simulation, and certainly you can learn things about conducting missions and about human machine interaction or interactions within the crew itself, small group psychology and things like that. If you want to get to the human environment interface, the human environment interface interaction, you need to be able to modify the environment and run experiments that show the changes in the environment and see how people respond differently to different environments or different design factors in the environment.
If we look at current research on lunar habitats, like the NASA's lunar safe haven concept versus the 1970s, 1980s conceptual designs for the lunar bases envisioned for the post-Apollo program, if the program was never canceled, where do you see the biggest shift in assumptions or priorities?
Well, the post Apollo lunar program concepts in terms of surface mission
Mhm.
was to have multiple simultaneous landings of Apollo lunar modules. And there were some concepts in the LISA study and in the Mimosa study. LISA was Lunar Exploration Systems for Apollo, and Mimosa was a Lockheed study. I don't remember what the acronym stands for. They were typically for 15-day or 30-day stays on the surface in the lunar habitats.
Mhm.
And everything was going to be supplied one time before the mission. There was no concept for in situ resource source utilization yet.
Mhm.
Everything had to come from Earth.
Okay.
And now for today, there's concepts of in situ resource utilization or ISRU,
Mhm.
largely for water and to crack the regolith to extract oxygen.
Mhm.
And those are really tough problems because the presence of water is actually very scarce.
Mhm.
Even in the so-called permanently shadowed regions, the percentage of water as an ore is less than 1% of the total regolith. And I just recently read an estimate that the cubic meter of regolith in the permanently shadowed regions would be expected to contain about 12 fluid ounces, which is about 350 milliliters or cubic centimeters of water. And that comes out to about 1/100th of a percent. And that's harder than digging up concrete on Earth and crushing it and processing it to extract the residual water of hydration.
Okay.
So that's going to be a very difficult process to implement.
Okay. Let me follow up on this. How should today's space architects adapt to those changes from bringing everything with us to space to, as you said, now we need to build the infrastructure through robotics and prepare the ore material, the main material through institute resource utilization, and then space architects have to do their job. How should they adapt to those changes, do you think?
Okay, well, the biggest shift overall is that we're moving from all government space habitats, modules, and spacecraft to commercial habitats.
Hmm.
And this means that there'll no longer be a single customer, which is NASA. This is a ship that flies not just to NASA, but also to ESA, the European Space Agency, and the Japanese Space Agency, JAXA.
Hmm.
And eventually, it may affect Russian and Chinese spacecraft and space stations as well. In terms of the content and quality of the work for space architects, there seems to be a parallel shift from pursuing functional advances to pursuing a stylistic emphasis on the appearance of space habitats and spacecraft. There have been tremendous advances in the capabilities of CAD systems, and the new generation of space architects possesses awesome skills in 3D CAD rendering. However, I am afraid that I have not seen a proportionally corresponding improvement in functionality, structures, and operations, with only a couple of exceptions. The two teams that have impressed me with the quality of their work are Search Architects with their Mars ice houses and Icon with their full-scale additive construction. Now, most importantly, the way space architects should adapt is to do the best work. Show the engineers that we have a better big picture approach to space habitat and spacecraft design than they do. Support the customers and the users of space modules of all kinds. Be humble. You cannot succeed in this industry as a raving egomaniacal starchitect. It's not about me. Downplay one's ego and show that you understand the user's needs better than the engineers do.
Great advice, Mark. Thank you. As the global space community shifts from more attention towards Mars, whether through national programs like China's or private ventures like those led by Elon Musk, we're still largely reliant on conventional chemical propulsion, which can make the journey anywhere from 6 to 9 months. In your view, what are the most pressing human centered design considerations and responsibilities for space architects when it comes to sustaining crews on these extended voyages, especially given the physical, psychological, and environmental risks that will arise along before they ever land on the red planet?
Okay, well, the most important thing is that human-centered design must be research-driven and evidence-based. There are a lot of pretty drawings of space habitats floating around, but whether or how they meet the crew needs is subject only to speculation. There is very little evidence to support these designs as doing anything new or better than what has come previously. That is why I shifted away from designing to research and development. You can come up with the best design in the universe, but unless you can prove that it is better than the conventional wisdom and the repetitive legacy designs, you are nowheresville. One area where I have recently focused is Eclipse first design for space architecture. Space architects cannot truly claim to design better habitats until they master the integration of environmental control and life support systems, Eclipse as we call it, in the overall architecture. Actually, if I may indulge in cynicism for a moment, for many of the new space habitat designs that I've seen, the young space architects don't even claim to have designed better habitats, just prettier ones.
Great. You came up with a mechanically passive method to shield the spacecraft's crew. You wrote the paper called the Water Wall Architecture that utilizes peripheral ice walls for long distance missions like a potential mission to Mars. Why water, and what does this water wall do?
Well, I had two separate projects. The first one was the Mars, or the interplanetary habitat from when was that? That was around 1997. And then the Water Wall's life support system was much later. It was 2012 or 2013. And they really had different functions in the sense that for the interplanetary vehicle, there was a water shield based on in a geometry of a truncated octahedron. And that provided I forget, it was either 30 centimeters or 50 centimeters of water shielding all around a habitat volume with a diameter of about 6 meters across.
Mm-hmm.
The water walls concept was one to develop an algae-based regenerative life support system. And I worked with the principal investigator, Michael Flynn at Ames Research Center, who is an expert in water processing. And those bags were not nearly as thick. Those bags were typically 5 centimeters. So there was a very small amount of radiation shielding there, but almost nothing compared to the 1997 concept.
Okay. As robotics and autonomous systems becomes more capable, how do you envision humans and robots sharing responsibilities in habitat construction on the moon or Mars?
Well, robots can do a lot of the work autonomously or by teleoperations to construct, deploy, and assemble structures, including primary structure pressure vessels, which are very difficult to make, by the way. But there does not seem to be much evidence that robots can do very much for detailed interior outfitting. And I speak from the experience of having done a project at an auto plant when I was a grad student at Michigan, where I visited the Buick Oldsmobile Cadillac plant in Hamtramck, Michigan, where they had this long assembly line called RoboGate where the robots were putting together the cars, or putting together what they called the platforms, the bodies and the chassis. Once they went through the 200 or more robots, then the human workers had to get in there and put all the small stuff in, and the wiring and so on. So the way I see it is that humans will need to be involved in setting up and activating interior secondary structures and the equipment, plumbing racks, submodules, utilities, and wiring that populate the interior. I mean, there may be some advanced robots that can do some of the interior work, but I think people will always be essential.
Let me ask you a follow-up question here. By secondary interior structures, do you mean the structures that will be assembled or set up in or under the radiation protection mound or lava tubes?
A secondary structure is inside the pressure vessel. The struts, the standoffs, that support racks or panelized compartments. That's what I mean by secondary structure.
Okay. Then let me ask you a question here. With advancement in manufacturing technology, are you in favor of assembling the secondary structure or a structure that you're in favor of a structure that is self-deployed? Also, are you with habitats with solid-state lunar structure or inflatable ones?
I think that it depends on how clever the designer is. I mean, we can make interior secondary structures that deploy, that unfold, that are hinged, that open up and expand. There are a lot of possibilities geometrically and mechanically.
Mm-hmm.
And as far as the inflatable versus solid pre-integrated habitat, or the
Mm-hmm.
what's called design for minimum risk habitat,
Okay.
I think both are viable. I think the inflatables have a lot of advantage in terms of saving weight and volume. But I think that if you're putting together a lunar base, you're going to have a combination of things. You'll probably start out with a construction shack, if you will, that is a pre-integrated, solid, hard habitat, which also serves as a safe haven. And then you'll have a class 2 inflatable habitat. And then from there, you'll probably try to build some in situ resource habitats. So eventually, as you build out a lunar base, there'll be all three classes of habitat of construction working together.
Okay, cool. Technology, material science, and space missions are getting more advanced and complex. So, Mark, you have a great bank of concepts that you have invented and designed over the last 4 decades and plus. Which of your earlier design proposals might be more achievable now, or you feel it's about time we build them?
Well, both. I think they've always been achievable, and it's about time we build them. Actually, some of my earlier designs are already in use. The spherical nodes in the triangular tetrahedral space station became the short cylinder nodes in the ISS, as did my patent on the cupola.
Mhm.
But the spherical relocatable nodes with 6 berthing ports that appeared in the Requirements Update Review number 2 in October of 1985,
Mhm.
those are now being used by the Chinese in the Tiangong 3 space station.
Mhm.
So it's in use, it's just not necessarily in use by the customer for whom it was intended. Now, as for the suit port, that's been built into a number of rover simulators, including the hazmat vehicle at Ames, Pascal Lee's Arctic rover simulator, and the University of Michigan's rover simulator, and there are others too. Now, the astronaut Michael Gernhardt has taken the suit port ball and run with it, developing several generations of full-scale working mock-ups of the suit port interfaced with rear entry suits. He built 2 suit ports into the JSC Lunar Electric Rover, which served as the NASA float in Barack Obama's 2009 inaugural parade.
Okay.
Meanwhile, many space architects have been incorporating suit ports into their habitat designs. The problem there is that they don't necessarily understand the complete concepts where the suit are not exposed all the time to the space environment with its dust and extreme thermal swings, but the suit ports are housed and protected in a secondary airlock. The University of North Dakota habitat mockup gets that right.
Wow, there's a lot to unpack here, Mark. So can you tell our audience what is a triangular tetrahedral space station, and why are spherical nodes important in your view or as per your research?
How many hours do we have? This goes back to Buckminster Fuller
Hmm.
in the way that he reordered the Platonic solids. Now, Plato, in the Dialogue of Timaeus, enumerates the 5 Platonic solids, the tetrahedron, cube, octahedron, dodecahedron, and icosahedron. And those are ordered by the number of hedra, the number of faces. But Buckminster Fuller took them and reordered them by the number of vertices and published that in his book Ideas and Integrities from 1963. And what that struck me was that we needed to look at geometric forms in terms of vertices first, rather than edges or faces. In thinking of space station module configurations, where initially we were looking at a square loop of 4 modules, I realized that we can improve on it by making it into a triangle. And instead of trying to butt the cylindrical modules up against one another, use a spherical node or hub at the corners, at the vertexes. And then once you do that, you're better off with a triangular configuration because the triangle is self-rigidizing. You don't have to make the corner joints structurally moment resisting.
Mm-hmm.
This self-rigidizing triangle is what we call pin jointed, and so the joints don't have to resist moment forces. So anyway, that's how I came to the triangular tetrahedral concept, where you'd have the edge of the triangular tetrahedron, you have the cylindrical module, and at the vertex you have the spherical node.
Okay. And those nodes, the spherical nodes, differ from the current nodes by, I think the current nodes are 90 degrees perpendicular to each other. The axis of the
Right.
nodes.
Well, yeah. Well, see, that's a whole other level of sophistication, if you will, which is that once you get into the geodesic geometry, the ports, the docking ports and their hatches end up being placed at non-right angles so that you can have a 3-dimensional tetrahedron, and you can have multiple tetrahedra connected to one another. But people who live on Earth live in an orthogonal world where everything proper happens at 90-degree angles. So then there's a whole discussion about how you make the connections. And one of the limitations in the way that NASA engineers and contractor engineers think about it is they think that you have to plug the berthing connection straight in like you're docking a spaceship. And what I realized is that berthing modules together permanently for one time is fundamentally different than docking a spacecraft, which is going to undock and then redock and undock and so on. So for a permanent berthing connection, you can join things laterally. In my triangular tetrahedral space station patent, I show a lateral docking mechanism that allows you to, if you wish, join modules at 90-degree angles, make a square without having huge problems with making the connection.
Mark, you also mentioned earlier suit ports. Can you share with our audience what suit ports are and the use cases for them?
Okay, a suit port is a sort of an airlockless airlock. Now that may be more confusing. When you're going out into space wearing a spacesuit, you have to make a transition from the interior of the module, which has a pressurized atmosphere, into the vacuum of space. Okay. And to do that, you need to be able to get into a situation where basically you pump out the air or you bleed off the air before you can go out into vacuum. And conversely, when you're coming back from vacuum of space, you need to be able to pressurize the environment in which the suited astronaut is entering the space station. Okay. And that's usually done in an airlock. That's the way we're doing it now on the ISS and the way we did it on Skylab. And what I realized was that it wasn't necessary to sacrifice or waste 2 or 3 or 4 cubic meters of air every time you pass through an airlock. But in fact, all you really need to do is have a very small volume between the rear entry hatch of a suit and a corresponding hatch from the space station. So there you have maybe a few hundred cc's of maybe a liter or 2 liters of air, much less than a cubic meter, like 1,000th of a cubic meter.
Okay.
And you can just sacrifice the air from that little interstitial volume, and it performs the same function.
For our audience, I would recommend you to read Marc's paper. It's called "Innovation and Tradition in Human Spaceflight Architecture." It has a more detailed description about the suit ports and the triangular tetrahedral space station. Marc, what is your favorite science fiction book and why?
Well, I wouldn't say that I have a favorite book, but I do have a favorite author. I would say anything by Ursula Le Guin, particularly The Dispossessed, comes closest to being a favorite. Otherwise, my preference is for classic hard science fiction, Jules Verne, H.G. Wells, Isaac Asimov, Arthur C. Clarke,
Mm-hmm.
Robert Heinlein. In fact, recently I wrote an essay, What Did Jules Verne Get Right in From the Earth to the Moon? That will become a chapter in one of the books I am writing.
Quick follow-up question. Who is Jules Verne, and can you share two things you think she got right from the Earth to the Moon?
Well, Jules Verne was a French science fiction writer in the mid-19th century who wrote some of the very first serious science fiction, and they tend to be hard science fiction, and the science plays an important role. I would say two of the things that Jules Verne got right was one, the size of the capsule
Mm-hmm.
is very close to what we have had with Apollo and with Soyuz and with the new, say, SpaceX Dragon 2
Okay.
crew capsule. Second thing is that chemistry for the life support systems.
Mm-hmm.
I won't go into the chemistry itself, but he gets essentially the same chemistry that we're using now in some of our environmental control and life support systems.
Okay, great. And you also mentioned that you are writing a book. That is fantastic. It's about space architecture, right?
Yes.
Do you have a title or a tentative title you can share
Well,
right now?
I have two titles, which is actually two books. The first one is called Foundations of Space Architecture,
Mm-hmm.
and the second one will be called Designing Space Architecture.
Okay. When can we expect a publication? Is it going to be published? One of them be published this year, or is it something for 2026?
I'm aiming for January of 2026 for Foundations, and
Mm-hmm.
then I'm not sure how much longer it'll take to finish designing space architecture.
Looking forward to reading them, Mark. Which major areas of research or development do you believe are critical for the next generation of space architects to focus on?
Well, I don't think that it's a question of major areas so much as that space architects must become critical consumers and users of research.
Mm-hmm.
To a certain extent, that implies that the architect becomes the researcher, as it did with me. Designing is certainly the most enjoyable, gratifying, and rewarding aspect of being a space architect. However, I found that to make my design succeed, I needed to provide the research-based evidence to support the case for them.
Mm-hmm.
Architects must learn about ECLIS, human factors and ergonomics, and human systems integration, which is not really the same thing as human factors and ergonomics or human factors engineering. And above all, systems functionality.
Okay. How about robotics? Where do you stand on this with regarding to space architects utilizing them?
I think robotics have a lot of promise that we're going to make use of robots for all kinds of things. I think that when astronauts are going out on EVAs on the moon, that they'll be accompanied by robots.
Mm-hmm.
We'll have safety robots that'll be bringing life support supplies along with them. We might see astronauts in suits with umbilicals connected to robotic rovers that are traveling with the astronauts. I think there's a lot of potential for robots working with people and working for people. But the real question is always, are the machines serving the people, or are the people serving the machines?
In your view, which core principles or skill sets are absolutely essential for students or professionals who aspire to become space architects?
But get the physics right. That's number one. Second of all, in terms of using research, understand statistics. In terms of doing drawings, learn how to represent all the utility and structural systems in a space module, spacecraft, or habitat. That means that it's more important to make drawings that show assembly and physical integration of the whole module than to make pretty interior renderings that hide the multiple systems that make the habitat possible. Most engineers won't care what it looks like. In fact, if you draw their attention to appearances, you risk them assuming that if there is something worth looking at, an architect must be wasting money. But the engineers will respect you if you take responsibility for locating and physically integrating all of their subsystems.
Okay, and if you had to name one or two immediate call to action for policymakers, educators, or the public to accelerate progress in human centered space exploration, what would it be?
Well, first, we need an alternate launch vehicle for the Orion spacecraft. The Space Launch System, or SLS, may or may not be a good launch vehicle, but in either case, it is far too expensive. NASA has been using the internal number of $3 billion to $4 billion for the cost of a single unreusable SLS launch, and that is only while using up the 16 surplus shuttle main engines.
Hmm.
Assuming the SLS goes through a total of 4 launches, the fifth one will need all new SSMEs, which will add a couple $1 billion more to the cost of each launch. Now, it is possible that the New Glenn or the Starship can be adopted to launch the Orion and maybe even the Falcon Heavy. However, those modifications need to start now if there are to be timely launches. Now, as for space architecture, I would like to see a Mars sample receiving lab and quarantine facility on the Gateway Space Station. This approach has been a viable concept for over 40 years, known as Project Antaeus. I published a paper on it a few years ago, and I have proposed a NIAC, NASA Innovative and Advanced Concept proposal for Project Antaeus, but I received a very mixed, polarized set of reviews, with some reviews totally positive and others totally negative, which is very unusual. The other thing is to develop a lunar lander that places the crew close to the lunar surface and accomplishes that without increasing the risk of overturning. I show examples of that kind of solution in a paper I wrote when I was at Northrop Grumman.
Okay. Can you quickly just say what was the positive and the negative, like polarized reviews that you received on the project Antaeus? And is it for collecting samples received from Mars?
It's for receiving samples sent from Mars, isolating them from the Earth, quarantining them until they're determined to be non-active biologically, or if they are active biologically, not to be a threat to life on Earth. It would be in near rectilinear halo orbit about the moon, and I proposed attaching it to the Gateway Lunar Space Station.
Okay, great. I'll have to look into it. Very interesting. So, looking back over your 4-decade career, what key lessons or principles do you hope to pass on to anyone pushing the boundaries of space exploration?
Let's see. If at the risk of repeating myself, do the best work, understand and respond to the user's needs, understand the demands on the engineers and come up with architectural solutions that support their designs and concepts, or better still, improve upon them. Support your design ideas with research. Take an evidence-based approach as much as possible. At the same time, don't be afraid to propose breakthrough ideas and take conceptual and cognitive risks. You should always be pushing the envelope to improve over conventional designs such as ISS modules and forced standoff racks.
What are some overlooked areas in the space industry that people need to start paying attention to, and why?
We need to focus on the human-environment interface, which I mentioned earlier. We need to begin conducting simulations for research purposes in which the variables lie in the environment. We need to be able to modify and adjust the environment and run multiple crews through these different habitat environmental variations. I proposed this approach in a recent paper, Lunar Daytime, in which the timescale would run the 14 days of lunar daylight. The emphasis would not be on long duration isolation and confinement, but what happens when we change the design of the habitat within well-defined parameters and where the researchers control these variables. We proposed that to the NASA Trish, but they didn't understand it at all.
Okay, finally, looking ahead, where do you see the extent of humanity's space exploration achievements 20 years from now? 2045, 2050?
I expect that for the next generation of space architecture, we will be focused heavily upon the moon, Lunar Gateway Station, lunar bases, and lunar habitats. I do not expect to see humans on Mars in my lifetime, at least not live humans.
Let me ask you a follow-up question to that. Do you ever think that a baby will ever be born up in space? Is this something achievable, or that's what will never happen in the next 50 years?
Well, you've asked me one of my favorite science fiction sort of questions, which is, have you read Isaac Asimov's Foundation trilogy?
Yeah.
Okay, so do you remember that on the capital planet, the planet Trantor,
Yeah.
there were 30 billion people. And planet was so crowded, there was only 200 square miles of open land, which was a park, and each citizen was allowed to visit it once in their lifetime.
Exactly. That's the royal palace for the emperor.
Right. So 30 billion people. How do you suppose they got there?
Yeah, definitely. Yeah, people will have to live and and give birth in space. Are we due to start looking at that kind of research, or like it's so far away, we have more other things better to look at?
Well, I think that yes, it will happen. I think that there are going to be medical issues, especially for, the pregnancy. The fluid shifts in the body will undoubtedly have an effect on the progress of the pregnancy. I don't know about the actual birth process without gravity. That could be complicated also by by being in space. But I would imagine that once people settle on the moon and try to live there on a permanent basis, that people will just do what comes naturally.
Okay, cool. So, Mark, before we wrap up, is there anything else you'd like to share with our audience?
Well, speaking to space architects now, new space architects and future space architects, it has more to do with the nature of the workplace than with space architecture per se. But in many organizations, there is pressure and demands to make all kinds of compromises, and some of these compromises are false and others are illegitimate. And there are always politics that can skew what you are doing and why you are doing it. So this I want to share. Always stand up for the truth. Don't ever compromise your integrity, even if it means negative consequences for your career within the organization or outside of it. Fight the good fight, like John Houbolt, arguing for lunar orbit rendezvous in the Apollo program. It may piss off management, but your colleagues will trust you, and so will the clients or users. And you will be able to sleep knowing that you maintained your integrity and stood up for what you know is right. Don't compromise yourself. Protect your sense of integrity and self-respect. Ultimately, that's all you have going for you in the workplace.
Mark, it's been an honor to have you here. Thank you so much for sharing your insights and expertise. And I can't wait to read your new books and maybe have you back here again and discussing them.
Okay, well, thank you. It's been fun.
And to everyone else listening, this is Omar Alayli podcast. Thanks for joining us and keep exploring.